Hey guys, so today we're going to be talking about some additional relationships between the trig functions. And the first one we're going to talk about are what are called co-function relationships. So this is a relationship that's going to exist between any trig function and its co-function. What I mean by a co-function is basically just the function with a co in the front of it. So this is going to be a relationship that exists between sine and cosine. This relationship will also exist between tan and cotan. And then lastly, this exact same relationship will also exist between secant and cosecant. This is a connection that you will always have between any trig function and its co-function. So what I did is I drew just a standard right triangle, and I just randomly labeled the sides as A, B, and C. And I labeled an angle as theta. And so I've labeled side A as being adjacent to theta, leg B is opposite to theta, and then C is the hypotenuse of this triangle. So that means that for angle theta, the sine is side B over C, and so for angle theta, the cosine is side A over C. All right, what I want us to do is swap between focusing on theta to focusing on this angle up here. And so this angle isn't in standard position, but you can absolutely still talk about trig for it because it's an angle in standard position. I would say we actually know exactly how big that angle is because this is a right triangle, right? If 90 degrees are already taken up here, these two angles must add up to 90 degrees. They must be complementary angles, meaning these two angles add up to 90. So like if this is 30, this is 60. If this is 40, this is 50. Regardless of how big theta is, I know that this angle up here will be 90 degrees minus theta. It will be the complement of theta. And so something I want to point out is you can still write sines, cosines, and tangents for this angle. You just have to acknowledge that though the hypotenuse stays the same, side A, which was adjacent to theta, that side is opposite the complement of theta. So this is opposite of 90 minus theta. And then the side that was opposite of theta, well, that side is actually touching. That leg is adjacent to 90 minus theta. Okay, so what does that mean? It means that if I wanted to try to write down what the sine of 90 minus theta was, if I wanted to write the sine of this angle, I would just need to go opposite that angle, so that's side A, and then the hypotenuse is obviously still C. Okay. And then if I wanted to do the cosine of 90 minus theta, the cosine of 90 minus theta should be the side adjacent to that angle relative to the hypotenuse, so that should be B over C. So an interesting relationship has emerged here. It turns out that the sine of theta was actually the cosine for theta's complement, because the side that was opposite theta was adjacent to the complement of theta. It also turns out that the cosine of theta was equal to the sine of theta's complement. And so this is actually always true. It is always the case that if you take the sine of an angle, that will be equal to the cosine of that angle's complement. And further, it's true that the cosine of any angle will be equal to the sine of that angle's complement. So between these two co-functions, the sine of one angle is equal to the cosine of the complement. The cosine of the angle is equal to the sine of the complement. Now I said that this co-function relationship actually worked for all the trig functions. And so I'm going to point out how that applies to another trig function. Let's say I tried to write down the tangent of theta. So the tangent of theta, I know, is just going to be the side opposite theta relative to the side adjacent to theta. So that's going to be B over A. And what I want to point out is B over A is also a trig value for the complement. It's also a trig value for 90 minus theta. So if we look at 90 minus theta up here, B over A would be the adjacent side over the opposite side. It would be the reciprocal. So it turns out that the tangent of theta is actually exactly the same as the cotangent of 90 minus theta, right? If cotangent is adjacent over opposite, that would also be B over A. So when I said that this co-function relationship works for any trig function and its co-function, that means it works for sine and cosine. It also works for tan and cotan. So I can say that the tangent of any angle is equal to the cotangent of the complement. And the reverse of that is also true. You can prove that with this triangle. The cotangent of any angle is equal to the tangent of the complement. And we don't even need to prove it. You're welcome to investigate the triangle. If it is true for sine and cosine, it is true for tan and cotan. It will also be true for secant and cosecant. So you can add to the list here that the secant of any angle is equal to the cosecant of that angle's complement, and the cosecant of any angle is equal to the secant of that angle's complement. This is true for any angle, even if it wouldn't fit into a right triangle. So these relationships remain true, even if we have angles that are like 280 degrees or 450 degrees. These relationships are actually true for all theta, and they work both in degrees and radians. So you can say that the sine of theta is equal to the cosine of 90 minus theta, but you can also say that the sine of theta is equal to pi over 2 minus theta. They work for all angles. They work in radians and degrees. The sine of any angle can be replaced with the cosine of that angle's complement, and that is true for all trig functions and their co-functions. The second type of relationship we're going to be talking about today are what I would call even and odd relationships. So basically, I just wanted to remind you of what even and odd functions are, what their properties are, and then we're going to see if we can apply some of those properties to our trig functions. So I'll remind you that an even function is one where f of x is equal to f of negative x, meaning putting in positive input and putting in negative input do the exact same thing. Even functions are ones where if you put in some number and you get out some output, the exact same thing should happen if you put in the negative version of that number. You should get out the exact same output. So these are called even functions because they behave like even exponents. A classic even function is the function y equals x squared, because it does exactly this. It doesn't matter whether you put in a positive or negative. Like if I put in 3, I get out 9. If I put in negative 3, I get out 9. Another example of an even function would be like the absolute value function. It's doing the exact same thing with positives and with negatives, and that'll always make it symmetric about the y-axis. The left side of the graph and the right side of the graph will look the same. So what I wanted to point out is that one of our major trig functions is even, and this clue about symmetry about the y-axis might have tipped you off to it. If you think about the graphs of all of your major trig functions, I will say one of them has symmetry about the y-axis. It's this function right here. You're maybe used to drawing it like that, but also it, of course, goes backwards like this. That we have a trig function that has symmetry about the y-axis, and that function is the cosine of x. So it turns out that cosine is even. And what I mean by that is putting a negative angle into cosine does exactly the same as putting a positive angle into cosine. So I'll show you an example of that. Let's say I took the cosine of 60 degrees. All right, so if you think about 60 degrees, I'll just draw a little picture here. Here's 60 degrees. Cosine is measuring how much it points forward. Got a little glare there. 60 degrees has a cosine of exactly 1/2. When I say I can prove to you that this is even, what I mean is the exact same thing should happen if I take the cosine of negative 60 degrees. Putting in a positive angle and putting in a negative angle should do the exact same thing. So if you look back here at my picture, negative 60 degrees, that just means you start at the x-axis and you go down 60 degrees. Here's negative 60 degrees. Notice both of these angles, positive 60 degrees and negative 60 degrees, both point forward the exact same amount. Cosine of 60 and the cosine of negative 60 are both 1/2. With cosine, the graph is symmetric about the y-axis. It doesn't matter whether you put in a positive or a negative. Cosine is even. And so what that means in terms of trig replacements, because cosine is even, it is the case that whenever you see the cosine of negative x, that is exactly the same as the cosine of positive x. Cos negative x and cos positive x are exactly the same. Okay, when it comes to odd functions, An odd function is one that behaves like an odd exponent, like x to the third, for instance. And so what that means is if you put in a negative, if your input is negative, the output will also switch negative. So for instance, 2 to the third is 8. That means negative 2 to the third is negative 8. Putting in negative input is going to produce negative output. So what I will point out is it is the case that more than one of our major trig functions follows sort of the rules of an odd function. And so you might be able to guess if I only put cosine over here, sort of like the other two biggies are probably over here. Let's look at these real fast. So if I look at a graph of sine real quick, we're used to drawing sine like this, of course. But think about if you drew sine on the other side also, it would look like that. And so if you sort of zoom in on any sort of given part of this, you can see that a sine graph, actually, it looks a lot like x to the third. It has this thing called symmetry about the origin, which is to say that if you flipped the graph side to side, it'd be exactly the same as flipping the graph upside down. You could spin the graph 360 degrees and it would look exactly the same. But perhaps sort of more simply for your purposes, it is the case that if you take the sine of a positive angle, it's going to do exactly the opposite of what would happen if you took the sine of a negative angle. So for instance, let's say I took the sine of 30 degrees. So the sine of 30 degrees is going to be a half. Let's say I then took the sine of negative 30 degrees. So negative 30 degrees, just going down a little bit, that is going to have a different sign. Specifically, it's going to point down, so its sign is negative a half. When I switched whether the input was positive or negative, the output also switched from positive to negative. This is true for sine. It's also true for tan. So for instance, if we wanted to look at the tangent graph real quick, something we actually identified as soon as we saw the tangent graph is it looks a lot like x cubed. The center of the tangent graph looks a lot like x cubed, and then it just repeats itself over and over and over again. But a tangent graph is also odd. I'll give you an easy example of this. What's the tan of 45? The tan of 45 is 1, yeah? What happens if I take the tan of negative 45? Well, that is the exact same slope, it's just that its slope is negative. So, whereas for cosine, if you have a negative inside cosine, it's exactly the same as if you had a positive inside cosine. It's clear that with sine and with tangent, if I put a negative inside the function, it makes the output negative also. How does that impact you? What it means is when you see the sign of negative x, you're going to want to rewrite it, kind of like we have up here for the definition of an odd function, as negative sine of x. The sine of negative 30 is the negative version of the sine of 30. Same goes for tangent. The tangent of a negative angle is the same as the negative version of the tangent of the positive angle. So for cosine, it does not matter if there's a negative on the inside. You can just get rid of it because cos 30 is exactly the same as cos negative 30. It's even. The negative on the inside does not matter. But for sine and for tangent, if you have a negative on the inside, you can just move it outside because sine and tangent are odd. All right, I just wanted you guys to see a big board of everything we've talked about so far, all of the replacements you can use when you're solving equations or simplifying expressions. I will provide you guys with a piece of paper online that you're welcome to print out, or you can write all this down, or you can just have it up on your computer. I would recommend having all of this reference information available when you go to simplify expressions and solve equations. We have the Pythagorean identities, which we've been talking about for the last two classes, as well as all the co-function relationships, that the sine of any angle is equal to the cosine of that angle's complement, and that's true for any trig and its co-trig, like secant and cosecant. Notice this is true for any angle, whether it's in degrees or radians. Earlier I wrote 90 minus theta. Here I've written pi over 2 minus theta. That's what it would look like in radians. And then you also have your even and odd functions, that because cosine is even, a negative inside cosine can just go away. So it is the case, for instance, that the cosine of negative 30 is just exactly the same as the cosine of 30. But that for sine and tangent, because they're odd, a negative inside the function can actually just hop outside, because the sine of negative 30 is the same as negative sine 30. So you've got all of this at your disposal. whenever you are solving an equation or simplifying an expression. Good luck!